The Agilent 7500 CE benchtop ICP-MS with octopole reaction system technology is revolutionizing ICP-MS. Its unique octopole reaction system removes spectral interferences, allowing ultra-trace measurement over the widest elemental range, even in the most complex and challenging sample types. Let's take a look at the key components of the 7500 CE. The sample introduction system consists of a nebulizer, spray chamber, and ICP torch. Ion generation takes place in a high-temperature 27 MHz plasma. Agilent's unique shield torch system reduces ion energy spread, allowing optimum ion focusing and increased sensitivity. The off-axis ion lens system ensures high ion transmission across the entire mass range, plus low background noise. The octopole reaction system is comprised of an octopole ion guide inside a pressurized reaction cell and can be operated in both collision and reaction modes for the removal of polyatomic spectral interferences. Mass filtering is performed by a high-frequency quadrupole with unique true hyperbolic cross-sectional rods for superior abundance, sensitivity, and peak separation. The advanced detection system provides 9 orders of linear dynamic range from parts per trillion to hundreds of parts per million. Let's follow the journey a sample takes from its sample vial through the ICP-MS to the detector. Sample is pumped from the sample vial into the nebulizer, where it is mixed with argon gas to form an aerosol. Larger droplets are removed from the sample aerosol as it passes through the cooled spray chamber, and the fine aerosol is swept into the central channel of the plasma. As they travel through the high-temperature argon plasma, the aerosol droplets are dried, decomposed, atomized, and finally ionized, producing a rich source of positively charged ions. The ions are extracted from the plasma into the interface through the sampling orifice, and then through the skimmer cone into the high-vacuum region containing the ion lenses and mass analyzer. Electrostatic lenses focus the ion beam and separate the positive ions from the unwanted neutral species by bending them into the reaction cell, the heart of the octopole reaction system, or ORS. The ORS is unique in using an octopole ion guide in the cell rather than the hexapoles and quadrupoles used in other cell ICP-MS systems. Octopoles are small, reducing the size of the cell and allowing operation at higher pressure relative to other systems. This results in more ion-gas collisions and greater interference removal efficiency, which also enables the ORS to operate in collision mode using pure helium collision gas. The larger polyatomic interferences collide more often with the helium atoms than the analyte ions and lose more kinetic energy. A potential barrier at the cell exit allows only the higher energy analyte ions to pass through to the mass analyzer. The low energy polyatomic ions are prevented from leaving the cell by energy discrimination. The analyte ions leaving the ORS cell enter the quadrupole mass filter and are separated based on their mass to charge ratio. Only the target ion is stable and passes along the axis of the quadrupole. The quadrupole scans rapidly across the mass range and passes each mass of interest sequentially to the electron multiplier detector. Ions strike the detector, and the resulting electronic signals are processed by the detector electronics and stored in a multi-channel scaler, creating a mass spectrum where intensity at a given mass is proportional to concentration of the isotope at that mass. To illustrate the interference removal power of the helium mode, a very challenging sample matrix containing these components was analyzed. Spectra were obtained for the mid-mass range, where most polyatomic interferences occur. This spectrum shows the matrix interferences that occur in normal ICP-MS. This spectrum was acquired in normal mode, that is, with no gas added to the cell. Almost every analyte in this mass range suffers severe polyatomic overlaps, making quantification impossible at trace levels. Now watch what happens when helium is added to the cell. All matrix-based interferences are removed. The remaining elemental peaks are due to parts per billion level contamination in the matrix. This is confirmed by the correct isotopic template fit. Helium mode has removed all polyatomic interferences simultaneously. Finally, adding a 5 parts per billion multi-element spike confirms all analytes are easily measured in this very complex sample matrix. The octopole reaction system offers the analyst a number of advantages. Its unique helium collision mode removes all polyatomic species simultaneously. No prior knowledge of the sample matrix is required. Unlike reactive cell gases, pure helium cell gas is inert and does not react with the analyte or sample matrix. Reactive gases are not suitable for multi-element analysis in complex sample matrices, since they react with the sample matrix, forming new interferences in the cell, which can bias analytical data. Helium collision mode enables rapid and accurate semi-quantitative analysis. More than 60 elements can be measured in a completely unknown sample in approximately 1 minute without the need to run calibration standards. The 7500 CE can measure mercury at single-figure parts per trillion, plus sodium at greater than 1,000 parts per million in the same analytical run. The calibration graphs show excellent linearity for mercury down to the 10 parts per trillion level, arsenic and selenium down to 100 parts per trillion, and sodium at 1,180 parts per million, all achieved in the same run. The ability to measure elements over a wide concentration range in a single analysis clearly demonstrates the power of the ORS. The 7500 CE with octopole reaction system sets a new standard for ease of use, accuracy, and productivity in routine metals analysis with its unmatched interference removal capability, high sensitivity, and wide dynamic range.